would like to thank the organizers for inviting me to present these lectures at this school here in Torino, in the first Reggio School. That's the title of the lectures, and there will be 3 lectures. So each lecture has a subtitle that will appear every day. The first lecture, as explained, will be a bit broader, and it will concern the explanation of what we mean by quantum gravity. So before that, I need to explain what is the quantum word and what is gravity. What is the theory that describes gravity? And of course, why it is important for science and, let's say, for society more in general. Even before I start with the slide, I would like to say that the lectures will have various levels. You can enjoy a first layer, if you want, of the pictures and to motivate you and to stimulate your curiosity, etc. And those of you who have a little bit more background can appreciate just a few formulas that will appear here and there, but you don't need to be scared about formulas. So these are there just for completeness and to make things more concrete, but it will be all in words and try to explain to you. I would like to convey, first of all, for this broad audience, first of all, that science is fun, in a sense, okay? So I would like to encourage you to join in this enterprise of science if you want, or just enjoy the show if you don't want to join science later on in life. Okay, so prologue. Our present vision of the universe and its laws is based on 2 pillars of theoretical contemporary physics. One is quantum mechanics that describes the infinitely small, the world at small distances. And the other one is general relativity, which is a theory of gravity. This word gravity will appear many times, that describes the world, the universe, at very large distances. So planets, stars, galaxies, and so on, up to the Big Bang that will appear later. These 2 theories account for nearly all current physical observations. That means that they explain exceptionally well the world as we understand it, as we see it, as we can measure in labs or with telescopes of various kinds. So in some sense, they are all we need, but we'll see that maybe that's not enough yet. So why should we care about quantum gravity? That's the main issue. Quantum mechanics, abbreviated QM, and general relativity, GR, are mathematically incompatible in particular conditions. I call them extreme. One such example is the Big Bang, which is the hypothetical start of the universe, depicted in this figure here, in the far past. And another situation where these 2 theories become strikingly in contrast are in the fundamental description, understanding of black holes, objects that will be the subject of the 3rd lectures in more detail, but they will appear here and more superficial level. Okay, so quantum gravity seeks to unify quantum mechanics and general relativity in a single consistent theory. Consistent means that makes mathematical sense and can be used in predictions for experiments and so on. More reasons for caring about quantum gravity is the fact that there are some mathematical problems with trying to combine these 2 theories, and that will be, it's a mathematical problem which refers as the problem of infinities. I will discuss that a bit more later and also tomorrow. And then we would like to have some guidance for future experiments, which in this case, as we think about, let's say, gravity, are observations, because we have to observe with increasingly powerful telescopes, or, the stars and the far away galaxies and so on. And hopefully, maybe we will in the future try to find some experimental observative effect of the quantum nature of gravity at large scales. And then here we go in some, I mean, these pictures here, I will try to sometimes warn you when the pictures are something real or something just graphical, and like for science fiction, like these two pictures here. This represents an object which is supposedly a wormhole, something that is only hypothetical as we stand. And maybe, understanding better and fundamentally the gravity in its fundamental nature will allow us really our civilization in the far future to evolve to the next stage. But many of you, or maybe it's not the case here, but for many people, often there is one question when you say you are working on something, you're studying something, one of the questions is, okay, but what are the applications of what you're doing? What in practice, what will be obtained? So the honest answer, which I want to give you here, is nobody really knows what could be the applications, especially of quantum gravity. But it's a more general answer to many questions, because fundamental research in science is primarily driven by the desire of understanding more and understanding better. And also, as I mentioned earlier, there is a part which is having some fun, right? You want to have fun while you're doing the work that you're doing. For example, before becoming the director of the famous Manhattan Project in 1942, during the Second World War, Oppenheimer was a theoretical physicist, like many of us, studying quantum physics and gravitational collapse of stars. And then, of course, he became famous, also thanks to the recent movie that appeared, quite a nice movie. But before the war, the Second World War, many theoretical physicists, like Oppenheimer, contributed to the development of these theories that were then used during the construction of the atomic bomb, without really thinking about applications or possible implications. And of course, I don't want to give a negative connotation to the research that was done at the time, because we have the atomic bomb, but we also have the nuclear energy, which is supposedly useful for society. Also, some other examples, which are quite different from the main topic of the lecture, but still, I want to give you the feeling of how science, fundamental science in particular, proceeds. So many applications that you give for granted in the society nowadays, they originate from fundamental research in general relativity, in gravity, if you want, the GPS that every car and every phone and so on has these days. And also modern medical diagnostic equipment, which hopefully no one would like to need, but in case you need, there are these powerful instruments, tools these days, like MRI, which originates from the studies of nuclear spins, basically a topic in atomic physics, or other things like the positron emission tomography, which comes straight directly from studies of high energy physics. Also, perhaps the most famous example, although it's a little bit more indirect, the internet, the World Wide Web, was invented by Tim Berners-Lee at CERN, the famous lab accelerator in Geneva, at the end of the 80s, as a system which was useful for the theoretical physicists to share their information, to exchange data, ideas, formulas, and so on. So, in some sense, we should all thank or blame theoretical physicists for the internet. Okay, plan of the rest of the lecture. So, we'll start as a sort of historical discussion to explain why we have this tendency and this desire to unify things, to make things simpler. And then I'll discuss in turn the main features of gravity and explain how is this related to essentially mathematical subject of geometry. Then I'll turn to the quantum world, and I'll try to stress how these two things, these two theories, these two mathematical frameworks are deeply different. And then back to the question of why do we need really quantum gravity in more detail. Okay, and then I'll end up with some preview of the next 2 lectures. Okay, so the story maybe could start even much earlier from Aristotle and so on, but let's start here in the 17th century with Newton, that unifies the laws of motion of bodies on Earth. If you throw a stone or you fire with a cannon and so on, with something a priori completely different, what governs the motion of planets in the sky, in the cosmos. So that's the famous Principia, right? And that's the main formula. That's one of the few formulas, but I'll use it now in a second to open a small intermezzo. Okay, so that's the famous Newton law. Force equal mass times acceleration. So, as I said, I'll use this to explain, but maybe I don't need for this audience, but anyway, for everyone, to explain what it means for a physical theory to predict something, right? So the prediction is not like Nostradamus, right? Let's predict something out of nothing. There is some logical process, and you have to go through it with mathematical tools, and then you can predict the future. So that's the simplest example, perhaps one of the simplest examples. The motion of a little mass attached to a spring, which is called in physical jargon harmonic oscillator. So that's the theory. This is the theory. Okay, the theory is Newton's theory: force equal mass times acceleration. Then you have to pick a particular type of force, and what models the force exerted by a spring is this linear relation here. Okay, so there is this constant k. This gives rise, if you combine these two equations, to a differential equation. You have to solve it. If you know how to do it, very well. If you don't do it, don't worry. It's a simple equation to solve, and it gives a law of how the position of this mass depends on time, right? So at any time, you can predict where is the mass, how it moves, with some oscillation with an amplitude, which is denoted A. And here I also noted the energy associated to this system. Now, the harmonic oscillator will be a recurrent theme in my lectures. And the physicists would understand why. Right. Now, proceeding in our historical excursus, another very good example of unification is electromagnetism that was due to Maxwell. And even in the word of this theory, you can see that something has been joined, right? What has been joined? The theory of electricity, right? Here is a battery. Everyone knows what's a battery. And the theory of magnetism. Everyone knows what's a magnet and has perhaps experimented even in primary school with some magnets, right? So based on previous work by other physicists, that's always the case. No one comes out as a genius that starts from zero. Everyone has to work based on the work of the previous people that worked, or together with some colleagues sometimes. Right? So Maxwell, based on previous work, came up with this set of equations, and this set of equations describe all phenomena of electricity, of magnetism, and even new phenomena that came out of this new formulation. Another milestone in the unification. Oh, thank you for moving here. I have more space. Another milestone in this path is the unification of the concept of space and time. And that happened relatively recently, about 100 years ago, with Einstein's formulation of special relativity. So Einstein did many things. I will not enumerate all the things that he did, but he's quite known for the theory of relativity, but somehow there are really two theories at the price of one. He came up with one theory which is called special relativity, and then later on general relativity, which will come in a second, in a space of a few years, right? So the breakthrough of the theory of special relativity is the unification of space and time, and the mathematical formulation of these two concepts unified comes with some consequences, right? So an important concept which is introduced in special relativity is the notion of metric. So how you measure distances. In a three-dimensional normal world, to measure distances, you pick a meter, right, and you measure the distance. And you know that all distances are positive. It can be some number, which is always positive, or zero if the two things are just close to each other. In space-time, there is an abstraction of this concept, and the measure of the distances is done with a metric which can be either positive, negative, or even zero. So that's a picture of how you imagine space-time, and you need some abstraction because it's a three-dimensional picture that represents a four-dimensional space-time, right? So the plane represents, you have to imagine, like three-dimensional space, whereas the vertical axis represents time. And you can see that there is some sort of asymmetry, right? I mean, you can just imagine, you see these cones, the light cones, it tells you which events are causally connected to each other or not. Another important consequence of the theory of special relativity is the extremely famous equation of E equal mc squared, namely energy and mass are the same thing. 10 years later, in 1915, Einstein completes his revolution of physics. It was really a revolution by formulating the theory of general relativity. Now, something new and apparently many things surprising will come out of this evolution of the theory from special relativity to general relativity. The key idea, one of the key ideas, a way to phrase it, is that the metric, this way of measuring distances, become itself a concept which depends on the point where you are. So if Professor Magnier has a meter and measures distance, we'll measure something different from Professor Castellani, who is in a different space, point of space, or space-time in general. Okay? So mathematically, this is encoded in this table. I can call it a table. It is called a matrix, if you want. It's you see, it's a collection of functions. There are, I put it here in red, 10 different functions, each one with its name, and they depend on these coordinates here. And Einstein proposes that the force of gravity is a consequence of how this metric behaves, and actually how this metric behaves, the different functions, actually, you'll see now in some pictures, they tell you how the space-time is curved, right? So that's a typical picture. Again, it's a representation in some three-dimensional image of what should be some four-dimensional situation. And then we have this fact that, in turn, the curvature of the space-time is due to the presence of matter. So it's a sort of circular thing, like in Italy we say that the dog that bites his tail. And if matter determines the shape of the metric and the metric determines how matter evolves, where do we start from if it's circular? So such problems in general, they are modeled by some differential equations. These are the tool that we use, the mathematical tool that it's used. And okay, these are called partial differential equations. And the particular set of partial differential equations that determines how this metric, what is the solution of the metric, you cannot take any metric that you want. It is fixed by some equations, right? And which equations, it is not something that you can read off somewhere, but Einstein came up with these equations by putting together some physical insight with mathematical consistency of its equations. And these are the very famous Einstein equations, okay? So here is a slide about Einstein's equation. If you don't like equations, turn off for a minute and then turn on back later. That's one of the features of the most beautiful equations in physics. They're extremely simple to write. They fit into a little box. Most of the physical equations, nice physical equations, they fit into a little box for the really fundamental ones. But they are deceptively simple as they are extremely complicated to solve. This is true for Einstein equation. It will be true for other equations that I will write later, Schrödinger equations, and so on. So let's see just what they involve. It's an equation. So first of all, there is a left-hand side and right-hand side. Something is equal to something else. So what appears here, you can see the metric itself, this table which I wrote. Then there is a constant, which is a Newton constant. And then this object here, called Ricci tensor, is a mathematical definition of the curvature. So it's a mathematical way of formalizing this picture. I mean, if you have to do some calculation, you cannot work only with pictures. You need some mathematical definition, and that's what this object R is giving to you. T is something that tells you how the matter is distributed. So if there is a star or there is a planet and so on. Again, it's a way to make this mathematically formal. As I said, finding solution to the equation is extremely complicated. And if you're interested in some particular solution, you have to wait to the third lecture and come to the third lecture where I discuss some solution. So, okay, now Professor Martelli, you're telling us this equation, okay, but what about gravity? Where is gravity? Well, in what sense this equation describes gravity? The idea is that when the four-dimensional spacetime is not flat, then the shortest path between two points, or spacetime points, is not necessarily what you think it is, which is a straight line. Right? So you learn in school, we all learn in school that the shortest path between 2 points is a segment on a line that passes through these 2 points. But that's not true. It is true only if the metric and therefore the spacetime is flat, which is the case in the ambient space that we experience, but it's not the case in this more elaborated concept of spacetime. And here is a toy example, which I think illuminates this concept quite well. So imagine to be on a sphere, and just imagine to be on Earth, right? Where we are. Now, if you want to go from one point here in Europe to somewhere in Africa, you can't really go in a straight line, simply, well, in this case, simply because you would need to dig a tunnel, and you cannot do it. You cannot pass through Earth, right? So you need to go through a curved path, and if you project such path on a plane, it looks like you're doing something really strange. You're not really going straight. So this is like a pictorial expression of this concept. The shortest path between 2 points is an arc on Earth, and these are called geodesics. And that's the reason why planes fly along this path. That's because it's the shortest way. And planes, they are companies and they want to save money. They don't want to go along long paths. So they go along the shortest possible paths to save fuel and so on. Okay? So that's the idea. Now you have to project this idea in a world which is four-dimensional, and it includes time, space-time. Any object, be it a star, be it a planet or an asteroid, with some mass or energy, including light, and something which will come back later, follows geodesics in space-time. So it goes along such paths which are dictated from how this metric is determined by solving the equation of Einstein. And that's the intuitive picture which often is used. Some heavy object, like for example a star, curves the space-time, right? You imagine like a sheet, and you put like a heavy ball on it, it will be curved. And then if you throw a little ball, it will follow a path which is not straight. It will go along this little well, and therefore it will deviate, right? But the trajectories appear to be deviated, but it's actually just following the shortest possible path on this sheet. And the same happens in space-time. So every object moves along geodesics. So essentially, it just follows the path of minimal friction, let's say, in quote marks. Okay, so there is such a theory. Let's go through some of the successes and surprises of the theory. So every theory, general relativity, but every physical theory, first of all, needs to explain all the observation until that point. And secondly, it can make predictions by following the logic, which I explained with the harmonic oscillator. So the first success of GR is to explain observations such as the precession of the perihelion of Mercury, which was observed already in the 19th century. So the orbit of Mercury somehow shifts in a way that is not explainable by Newton laws. So Kepler would not explain such observation, but general relativity does. Then, moving on, observations at the beginning of the 20th century show that most galaxies appear to be moving away from each other. So they move away from our galaxy, which is called Milky Way, and also away from each other. To explain, so this observation was explained by Friedman and another physicists at the beginning of the 20th century using Einstein equation. So Einstein gave them the equations, and then different people, by solving the equations, found different solutions explaining different phenomena. Okay, so this observation then led to a model that predicts that the universe is expanding, right? A concept which is a bit difficult to grasp, so we'll not try to explain it, because it's not necessarily expanding as we imagine, because there is nothing to expand in. But anyway, roughly speaking, let's say. And then if you extrapolate this to the far past, then if it is expanding, then there must be a point where everything started. And that's called the Big Bang. Okay, we'll come back to that as well. So that's another prediction of general relativity. The universe started in some point. Now, after the formulation of general relativity, essentially all the known physical theories at the time had been geometrized, explained in terms of geometry or some differential equations and so on, and then include mechanics and also electromagnetism and gravity. So one feature that all these theories share, although they describe very different physical phenomena, is that they're all deterministic. So you say some initial condition, you say where the mass attached to the spring is at the time t equal to 0, and then you solve the equation and you can predict where it is in the future at any time in the future with 100% probability. However, a new revolution in physics was about to shake the world, and that's quantum mechanics, the subject of the second part of the lecture. And that's a famous quote from Einstein. Now, actually, I'm not a historic of science. Maybe someone knows the history better, because if you Google the quote, you'll find different versions. So I'm not quite sure what is the completely true version. But in any case, he certainly said something like that, and he certainly had such a thought. Einstein was not happy about quantum mechanics, right? He didn't like the idea that physical theories are not deterministic. So let's see what is quantum mechanics. Now, let me make sure that I started 15 past, right? Something. Okay, so at the beginning of the 20th century, certain experimental results, observation, could not be explained with all the known theories. And such theories, by definition, are nowadays called classical, right? Just as opposed to quantum, which is the new theory which we are about to discuss. These are famous observations, the two-slit experiment, with a phenomenon of so-called interference that underlies the fact that light somehow behaves as a wave. And also the observation of by Planck of how the certain radiation observed in from the cosmos is behaving. Okay, now the key idea to explain such phenomena, which could not be explained with mechanics, electromagnetism, or even with gravity, with general relativity or special relativity, is to introduce something completely new. And this new idea that turns out to be successful is that energy and other so-called observable, like angular momentum and so on, but let's speak about energy, cannot take any value, right? But it comes in lumps, in little packets, which are called quanta. That's the reason of the name quantum mechanics. For example, here you have a famous relation. The energy is also related to the wavelength of let's say of some light okay, I didn't say this well. That's a relation that relates fundamental constant like energy, the velocity of light, which is c and is constant, and this fundamental constant which was introduced by Planck. I will see later a more explicit version of this relation where the quantum nature, this discretization becomes more clear, more transparent. So quantum mechanics evolved in the first 30 years of the 20th century, and somehow one can put the official birth somehow in this famous conference where many eminent theoretical physicists at the time, you can see also Einstein in the middle, notably Heisenberg, Schrödinger, and many others gathered together to discuss this new theory. So what is this new theory? The mathematical language is completely different from that of classical physics, right? It does not use the concept of geometry that we explained earlier, but it involves things which are called operators, and they live in some so-called Hilbert space. So these Hilbert spaces are infinite dimensional version of what is called in mathematics vector space. And the object that they describe are these, this is a picture of a vector, okay, which is typically labeled with this symbol, which is called a cat. And the physical observables, like the energy, as I said, or even the position or the momentum, angular momentum, and so on, are related to the spectrum of these operators. So the spectrum is a word which comes from chemistry, I suppose, and it tells you, you can see that there are some discrete values that these objects can take, okay? That's one version due to Schrödinger. There is another version due to Heisenberg, which is fully equivalent. This basically encodes quantum mechanics. This is the quantum mechanical counterpart of Einstein equation. It's the equation that governs any quantum system. You have just to say, what is this object here? That's called the Hamiltonian, and put a specific Hamiltonian, as I said earlier when I said pick a force. Here, pick a Hamiltonian, and you'll have a differential equation for your system. Okay, so let's make an example, and you can see the harmonic oscillator comes back. If you consider precisely the same problem of the harmonic oscillator, but you put in this quantum version, you obtain a completely different solution. So earlier, you remember there was a sort of a cosine, and then you have some evolution, right, like some oscillation like that. Here, you start with the same system, but you interpret in this new framework of quantum theory, so with the specific mathematical rules, which I told you about these Hilbert spaces and so on. And then the output is that the energy is in fact quantized, right? And so here I depict the various levels. So n is an integer number, and you can see there can be only lumps, right? So n can be 1, 2, 3, 0, 1, 2, 3, and so on. So to make it to come back to what I observed earlier, and quoting another famous recent physicist, Sidney Coleman, the career of a young theoretical physicist consists of treating the harmonic oscillator in an ever-increasing level of abstraction. Right? So the harmonic oscillator is not just a toy example, which is suitable for the discussion of today, but it turns out to model a huge amount of real physical system. I'll come back to that also tomorrow. Then there is an array of striking, spectacular, mind-blowing, call it as you want, consequences of these theories. So not only it introduces an entirely new paradigm in physics, but it leads to numerous puzzles, paradoxes, or apparent paradoxes, and debates, even philosophical debates that started 100 years ago and they're still ongoing, about the interpretation of reality, which have both practical, as I said, and philosophical implications. So concepts such as uncertainty, right? So in quantum theory, there is no 100% probability of an outcome of some, say, experiment or even some measurement, let's say. Another consequence is called entanglement. So it apparently leads to some sort of action at a distance. You observe something here, and that affects something which is distant light years from here. And then another one, which I'll dwell a little bit more, is the concept of superposition, right? So I'll explain a little bit more what this picture is. So is your cat alive, is dead, or a bit of both? That's very strange. As I said, if you start thinking about these things, there are some philosophical implications that you can go on and discuss, but there are also many practical applications. And some of these applications, I think, will be discussed in Leonardo's lectures, Professor Castellani's lecture. Oops, oh, this is too quick. Yes. All right. So Heisenberg, one of the founders of the theory, argued or proposed that there is a limit in the accuracy in which you can measure, say, the position and the momentum, which is essentially related to the energy of a particle. Okay. So you cannot measure this simultaneously. And here, well, here is just a little cartoon which I find on the web. You can read it for yourself. And that expresses the fact that while classical physics is deterministic, quantum mechanics is intrinsically probabilistic, right? So it's not just the fact, an artifact of the fact that you can, if you do a better measurement, you will find better accuracy. It's just an intrinsic limit, an intrinsic feature of the theory, which is quite hard actually to accept. So if you don't understand it, don't worry. No one really understands it at a deep level. Okay, so a physical state is represented by this weird thing of different superpositions, and I'll put a picture that can depict what is a superposition of two different things, with different possibilities, with different probabilities associated. And okay, that's the famous so-called Gedanken experiment or thought experiment that was due to Schrödinger, again, one of the founders of the theory. And you can see here, before even reading this, that's a picture, that's an image. So you have a cat which is simultaneously alive and dead. So, by the way, this was never actually done as an experiment, just I don't want to worry about animals. So just imagine closing a cat in a box with some deadly poison inside. And then, I'm just making a simple version. And then you don't know, because you close the box, you don't know whether the cat is dead or alive, because he might have eaten the poison or not, so you don't know. So until the box is closed and you don't know and you don't observe it, then you cannot tell whether it is dead or alive, right? And therefore, the theory tells you that it is a little bit of both. You have to assume that it is a superposition of these two possibilities. It's not dead or alive, it's 1 over square root of 2 alive plus 1 over square root of 2 dead. Okay? That's the takeaway message. That's the concept of superposition. Oops. Moving on. In this, again, taking this historical view, first half of the last century, quantum mechanics, and then this evolves further. And other theoretical physicists, notably Feynman, Dirac, and others, developed, using these ideas of quantum mechanics, they put together with electromagnetism and other fundamental interactions in what is nowadays called a quantum theory of fields, quantum field theory. Roughly speaking, you can think of a quantum field theory as an infinite collection of quantum mechanical systems. So if you had one spring, let's say this is one spring, and you thought that was complicated to solve, now think about infinitely many all joined together. So you can think how you can see how the complication increases considerably. And there are new difficulties, new technical issues that one has to solve in order to address this. One problem, which I mentioned already, is the problem of so-called infinities. What does it mean? It means that if you start making computations, and if you know what is an integral, at least, you have seen what is an integral, and you try to compute this integral, you'll find that these integrals are infinite. Okay? So they don't make sense, and when they don't make sense, you don't know what to do. The theory, we say, it loses power of predictivity. It becomes useless. Okay, so what? You're telling us now that all these quantum field theories are problematic? Well, no. Some of them are problematic, some of them are not. Okay? So that's the main dichotomy. So physicists came up with a systematic method to deal with this problem, and it's called renormalization, whatever. Okay? So given the quantum field theory, you pick one. There are two options, roughly speaking. Either you can apply this method, and then the theory is said to be renormalizable. You see, there is a physicist here, Feynman, which is happy, just to say, okay, when your theory is renormalizable, you're happy. If the theory is not renormalizable, and here I used a picture of Oppenheimer sad, then you're sad, because your theory cannot be used. Okay. Now, given this fact, I point out that in 1999, the physicists Toft and Veltman received the Nobel Prize, I'm not talking about just some small prize, for the proof of the renormalizability of gauge theories. What are these gauge theories? Well, gauge theories are essentially a glorification of electromagnetism. So there are theories that describe electromagnetic phenomena, but also interactions such as the weak interactions, which are, for example, responsible for the fusion of nuclei in the stars, or the strong interactions, which are responsible for the atomic energy. And all these theories were, again, this word unified, okay, unified into a single quantum field theory called the Standard Model. And you'll hear definitely more about the Standard Model in the lectures, I believe, by Eric, then, if I'm not wrong. Okay, so given the course of history of theoretical physics, which we looked at the beginning, right? Newton, Maxwell, and so on. It would be natural to expect that at some point we would like to put quantum mechanics together with general relativity and make a quantum version of general relativity. However, it turns out that a head-on approach fails. It doesn't work. So GR cannot be promoted to a quantum field theory, and one of the main issues is really this problem that there are infinities that you cannot make sense of. Okay, so it's the case of being said, and okay, if you don't come up with a new idea, that's it. But before trying to come up with new ideas, okay, let's wonder, okay, so what? After all, general relativity and quantum mechanics work extraordinarily well. So I explained that they describe all that is known, all that is observed, and there are spectacular consequences. I mentioned atomic energy, GPS, and whatnot. So why should we bother about unifying them, really? And here I go back to the kind of more conceptual or more philosophical side. And I remind you again that science is driven by the search for unity, first of all, or simplicity, or elegance, to paraphrase famous authors like Brian Greene, okay, The Elegant Universe, or this other famous author, Hawking, who wrote a book called The Theory of Everything, right? If you have a theory of everything, it describes everything. So it's really one theory that describes everything. What these other two pictures are. So here, this is a picture of Occam, and you may have heard this in your studies of philosophy in school, so-called Occam's razors. What has the simplest explanation is likely to be the closest to the truth. Here is an example. This is an heliocentric system, an heliocentric model of the solar system, and this is a geocentric model. Okay, Copernicus versus Ptolemaios. Which one is simpler? You tell me. Okay, if you're not convinced that you need to find a unified theory, I'll try to give you some other reasons. So other reasons for caring about quantum gravity. Observations suggest that the universe started about 14 billion years ago. There are an impressive amount of data nowadays. For example, started in the beginning of this century, collected by this probe, WMAP, which represent the so-called microwave background. And that's a remnant, we regard this as a remnant of the Big Bang. So what happened 14 billion years ago, we can still observe by making measurements nowadays. But that doesn't mean that we really understand what happened here, right? And as this picture suggests, at this initial point, at the Big Bang and immediately afterwards, where immediately could mean microseconds, seconds, I mean, some amount of time. The quantum effect, so here it's written quantum fluctuations, quantum effect are important. So we would like to understand really the Big Bang better, assuming we can do it. I'm not sure, I don't know. But if we can understand it better, presumably we need to understand the quantum nature of gravity. Other reasons, more observation, the dark side, one of my favorite franchising in movies. But here is just it's a joke, right? Because we talk about dark matter and dark energy. So the large-scale structure of the universe we see today requires postulating the existence of dark matter. So if you want to explain the observation with general relativity in the very large scale, you need to postulate something that actually we don't know what it is. I mean, the name dark, it means because, first of all, it does not emit light, and it conveys the fact that we don't really know what it is. And similarly, there is another entity, another thing, which is called dark energy, which should explain, again, it's needed to explain why the universe appears to be also accelerating, not only expanding, but even accelerating. Okay, so today, the universe supposedly should be composed. This is this light blue is the fraction that made us and can be observed, and the rest is mystery box. Okay, so maybe general relativity is not quite the correct ultimate theory of gravity. Another reason for caring about quantum gravity is black holes. What is a black hole? Well, for today's lecture, but much more will be said in the third lecture, is a one-way cosmic sink, right? That's a picture of a sink. You can go in, you cannot go out. And when you go in and you reach this apex of this sink, of this funnel, then quantum effects, again, become important. If you take two black holes back to back and you glue them together, you obtain what is called a wormhole. Okay? A wormhole is supposedly something where you can go in and then come out in a completely different region of the universe, space-time. I want to make an important disclaimer, and it has to be appreciated by everyone. Black holes have been observed in the universe. Third lecture, you'll see a lot about it. Wormholes not. Okay, so these are observed. These are just theoretical constructions, but you never know. So, going to the end of the lecture, hypothetically, through a wormhole, we might be able to communicate with extrasolar or even extragalactic civilizations, if they exist. And here are two pictures. All these three pictures are just from movies or artistic pictures, nothing real. That's a picture from Stargate movie in 1994. And they used a wormhole that they created with some alien technology in a lab, and then going through this wormhole, they were able to navigate the universe. A more realistic, in a much more realistic movie, in fact, which I'll talk about also in the other lectures, Interstellar, 2014. Here you can see that a wormhole actually is not really this funnel that normally it's depicted, but it looks, if it exists, it looks a little bit more like something three-dimensional. It looks a bit more like a planet, if you want, a star. Except if you go in, you come out in a different region of space-time, at least in theory, right? So in a far future, maybe our descendants, whether they're human or not, it doesn't matter, they may be able to travel through these wormholes to distant stars and hopefully find a new home for them, because as you all know, certainly the solar system will have an end at some point, okay? So that's really to give you the inspiration, let's say. This is more in the science fiction side, far future, but you need to do fundamental research in order to elevate, as a human society, and go to next stages. And there might be surprises. So something like this might happen on something completely different we could not even imagine. I think I'm done for today. I finished. So I thank you very much for your attention.